Welcome to Module 4. In this lesson, we focus on measurement validation, filtering, and sensor confidence. In the field, a number on a BAS graphic can look clean and professional while still being wrong. The sensor may be drifting, the input may be scaled incorrectly, the network point may be stale, or the value may be mapped to the wrong object. Before a controller can make a good decision, the measurement chain must be trustworthy. After this module, learners should be able to define the language of measurement confidence and apply it in real BAS work. The objective is not only to know the definition of accuracy or plausibility. The objective is to decide whether a value is safe to use for control, reset, staging, alarms, analytics, and reporting. We will also cover filtering, fallback, substitution states, and recovery behavior when a sensor cannot be trusted. The core concept is that a controller controls from the measurement it is given. The physical condition exists in the building. The sensor responds to that condition. The signal travels through wiring, input scaling, controller conversion, network mapping, and finally appears on a graphic or trend. Every stage can introduce error. A professional does not trust the screen first. A professional verifies the measurement chain from the physical process upward. Before troubleshooting, separate the measurement terms. Accuracy is closeness to the true condition. Precision is repeatability. Resolution is the smallest increment the system displays. Drift is slow movement away from the true value. Plausibility asks whether the value makes sense for the process and operating mode. Quality tells us whether the point is online, fresh, and not faulted. High resolution is not proof of high accuracy. A good measurement should pass more than one layer of review. First, is the point online and fresh? Second, is the value within a possible range for the equipment and mode? Third, is the rate of change physically reasonable? Fourth, do related points agree with expected physics? Fifth, can a trusted reference or redundant value support the reading? One good status flag is not enough when the value drives important control decisions. Filtering is useful, but it must be used carefully. A raw sensor trend may contain noise or short spikes. A filtered trend can be easier to use, but filtering also adds lag and can hide important movement. The question is not whether the trend looks pretty. The question is whether the filtered value still represents the process well enough for the decision being made. Do not use filtering to hide poor sensor location, grounding problems, unstable equipment, or bad measurement technology. A useful design separates the numeric value from the validity state. The number may still be displayed, but the control logic should know whether the value is good, suspect, bad, or substituted. Good means the checks pass. Suspect means the value needs caution. Bad means it should not drive automatic control. Substituted means a fallback is being used. Operators should be able to see that state clearly. Hidden fallback creates false confidence. When a sensor fails, the sequence needs a defined response. Sometimes the system can hold the last good value for a short bounded time. Sometimes it should use a conservative fixed fallback, a redundant sensor, or a safe operating state. Optimization may need to be disabled and returned to a fixed basis. Whatever the response is, it must be visible, alarmed when appropriate, and documented. Holding the last value forever is rarely acceptable because the building continues to change. A shared outdoor air sensor is a good field example. One value may influence economizer enable, chilled water reset, heating water reset, optimal start, and reports. If that value fails silently, many systems can make bad decisions at the same time. The validation design should check communication, update age, range, rate of change, and comparison with another source. The fallback should prevent one bad sensor from driving multiple systems. Most sensor confidence failures come from trusting only one layer of evidence. An online point is not automatically a valid measurement. High resolution does not prove accuracy. Filtering can hide the symptom without fixing the source. A bad value can drive resets, staging, alarms, and analytics. A believable wrong value may be more dangerous than an obvious failure because people keep trusting it. Use a structured diagnostic method before accepting a measurement for control. First, define the decision that uses the value. Second, trace the chain from sensor to graphic. Third, check plausibility against range, rate, relationship, and operating mode. Fourth, compare the value to a trusted reference when the risk justifies it. Fifth, document the confident state and the action taken. This prevents guessing and protects the sequence from bad evidence. Best practice is to make measurement confidence visible and repeatable. Validate quality, range, rate, relationship, and update age. Show suspect, bad, and substituted states for important values. Filter only for the process and the decision being made. Define bounded fallback, alarm, recovery, and documentation. Calibration records should include as-found value, as-left value, tolerance, reference instrument, date, and impact. This turns sensor trust into documented evidence. This module gives us a professional method for deciding whether a BAS value is safe to use. Trace the complete chain. Check plausibility using physics and related points. Filter carefully so noise is reduced without hiding real behavior. When a sensor becomes suspect or fails, make fallback visible and bounded. The principle is simple. Invalid or suspect data should degrade optimization before it degrades safety or basic operation. For the knowledge check, the best answer is C. A chilled water valve at 100% with poor coil response does not automatically prove the coil is bad. The first professional step is to verify the measurement chain and physical process. Check sensor location, scaling, flow, operating state, water temperature, and uncertainty. Only after the evidence is trustworthy should we name a component failure or change the sequence.